Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 14 and we're going to look at the second of our statistical tests, the chi-squared test. This time you need to apply appropriate statistical tests of confidence to a data set including, but not limited to, the chi-squared test. The chi-squared test is a test that we perform on two ranges of data to determine whether observed results match expected results. Bruce and Bruce describes the chi-squared statistic as a measure of the extent to which some observed data depart from expectation. Mathematically, it's the square of the z-scores, and the chi-squared test is used to compare frequencies in particular categories. These categories should be mutually independent, that is, one subject cannot be in more than one category, and it includes a number of degrees of freedom that we've talked about before, which is the number of categories -1. This is a common test that's used for categorical data, and it can help to figure out if there's a significant relationship between two categories, like whether a specific teaching approach impacts student performance in different science subjects. The null hypothesis would assume that the experimental data would not differ from the theoretical data. That is, another way of saying the observed results are the same as the expected results. Now, I've given you a little example of some data that I collected that this is probably not the ideal way to use this particular test, but the important thing is that you get some practice in playing around with all of these different types of tests. And in fact, we've got some numbers for one of the previous examples that we looked at with the M&M counting data, and that's another one that you can look at in terms of difference between observed and expected, particularly if you're looking at something like the relative numbers of different coloured M&Ms that you would expect in a packet. So we might look at them a little bit later. But for this one, I looked at the different ways that teachers preferred to learn new ways of using technology in the classroom. So you can see I had a number of different categories here, from attending educator conferences, completing university coursework, school level or non-school level workshops or private vendors, learning on their own or from peers or from students, and then using a range of different other sorts of areas like user forums, listservs, help files, and web-based training, that sort of thing. I used descriptive statistics to give me an overview of some of the important measures. One other important thing about this is that all of the respondees had to rank each of these in an order of their preferred way of learning. So if they were going to do some training, what would they prefer? So number one was their top choice. Now, interestingly, with this particular series, they didn't have to number all the way to 12, although you can see for a lot of the categories they do go to 12. But the important thing was that we turned each of these categories, these ordinal data, 1 is the top choice, 2 is the second, 3 is the third. So we were able to find a mean score. In this case, what you're looking for is a very low mean. A low mean is a highly ranked score. So obviously, if every single person ranked a particular strategy as number 1, it would have a mean of 1, and that would be the most popular way of learning how to do something. Part of the job that you will be doing with your report is to explain, if you have manipulated your data in some way, what that actually means. Now you can see there is a mean score, but you can also see I've got modes. So modes are the most common scores. So the most common number that was used to rank each of these different areas of training. So, and you can also see that the mode is actually appearing on my graph there. So you can see something like learned on my own has a mode right down there close to 1, which is saying that's the preferred way. That's the way that most of the respondents who included that put is their preferred way of learning. Whereas something like list servers, not used very often and really only categorized by those who went through and numbered everything from 1 to 12, and where they did, the list servers came in at around number 11. That's their mode. So that gives you a little bit of an explanation of these kind of descriptive statistics that you're seeing. Now, I don't think you're going to have to calculate the test statistic, but it's here anyway. What we're trying to do is we're looking at a range of different categories. So these can be simple categories such as the preferred training method and the mode, say, or the average or the score, the number of the total number altogether, which I also calculated. Or it could be different scores with different category ranges as well. So you may find that you've got row totals and column totals. And when this is the case, you may have to sum both of these together. The main thing with the chi-squared statistic calculation is we're looking at the difference between our observed counts and our expected counts. The simple thing with this formula is if we were to observe every count being the equivalent of what we expected, then O minus E would be 0. Square that, still 0. Doesn't matter what you divide it by, it's 0. So the chi-squared statistic can be 0, but it can also be a deviation away from that. Like we looked at with the t-test, there will be a test statistic, but that test statistic then needs to be compared with a table of values and the number of degrees of freedom. In this case, there's 2 different groups that we're summing here, so you've got to consider both in your calculation of degrees of freedom. And then what you want, ideally, is for your statistical analysis program to spit out that number for the p-value. And fortunately, Excel will do that. So for example, I've just transferred some of this information into something that might be a little easier for us to use in terms of the application of the chi-squared test. So you can see I've got my categories. So these are my categories. These are all the different ways that teachers identified ways that they could train in order to improve their skills in the use of ICT. Then I've got an average here, the mean scores, which tells you roughly where each of these came in. So I can identify a score here, for example, of learning something on my own, which is the way that the majority of the teachers preferred, or learning from peers. That was another one that was quite popular. Whereas something like our list servers had a very big mean. The problem with trying to use the chi-squared test is you need to be very careful about scores that look like continuous scores, because that's where, when we look at some of the assumptions around the chi-squared test, it can come out not quite as it should. Now, ideally with your null hypothesis, the mean of the observed is equal to the mean of the expected. So that's kind of the overall way that you're looking at expressing this. Likewise, your alternate hypothesis will just be that that's not the case. And it may be that your observed values are higher or lower. In a situation like this, you might find that some of them are higher and some of them are lower. And so we kind of have to consider a few things when we're looking at analyzing these particular results. So just to give us some numbers, let's actually just focus on the mode and see what we get. If you're using Google Sheets, you can just type these formulas straight in. I gave you the one for the t-statistic, and here's the one for the chi-squared test. The key here is you're looking at the observed range. So you need to have your set of values with an observed range, which is obviously the data that you've collected, and your expected range. And that's going to be what you calculate that it should be if there was no intervention, if there was no difference between the groups, if you wouldn't expect any difference. In Excel, you can see one of the main things with Excel is we've got to put the equal sign in, which is an indication to Excel that there's a formula coming. The nice thing with Excel is it will actually allow you to work through each of these a step at a time. So just to put some numbers together to see what happens, you can see what I've done is I've transposed all of that data from the modes into my observed data. And then you can see in my expected data, what I've said is that if there's 51 in total, that's my kind of value from the modes, from the sum of the modes, then I can look at the expected data that I have of a value of, say, 4. And then see what happens when we put all of these together. So obviously, my null hypothesis is that there will be no difference, that people will rank all of these in any random order. They should all come out to the same rough average, and of course they don't. And statistically, is that important? So you can see my value here. So what you get with Excel is you get this p-value, which is kind of nice. And then we're always going to compare this with our alpha value, which is our test of significance. And in this case, we're going to continue to use the value that we've used previously, which is our 0.05. And here our p-value is less than 0.05, it's 0.03. And so therefore we could actually reject our null hypothesis and say, yes, in fact, there is a difference in this case. We do find that the difference between these values, some 1s, some 2s, some 7s and 11s, they are significant. So there is actually a real difference that we've seen in the way that teachers have nominated how they would prefer to learn new technology. So what about our M&Ms example? Well, when we looked at the calculating of the colors for the M&Ms, you can see that we worked out that there was, when we did our t-test, a significant difference between some of the colors, but not between others. So could we use a chi-squared test on something like this? Well, we could. And the simplest way to do that is just to look at the average values. So these are the average values that we've observed. If we were to simply assume that there was equal numbers of each color in each bag, what would we expect? Well, what we would expect is that from the average number that we get in the bags, that there would be an equivalent number in each. So that means our expected would be exactly the same. So could we do a chi-squared test with this? Well, yes, we can. So what we do is we find a spot. Now, we don't actually need to go into our data analysis tool this time because this is a straightforward test. So Excel has this in its formulas. So if we go to statistics, we go to chi-squared. Here's our chi-squared test. The nice thing with Excel is that it walks you through everything. So my actual range is the actual values I got. So I'm going to select them here. So that's my red, green, blue, yellow, brown, and orange. And so then I want my expected range. So remember, my expected range is based on all of the colors occurring with the same frequency. Now I do have decimals here, and it's probably better if I have all of these as whole numbers. It just works a little bit better. And what you can see is when I hit OK, I get this value here. So the value I get for my chi-squared is 0.0184 blah blah. This is a p-value, and therefore this p-value is much less than the 0.05 that my alpha value would have. And so once again, I can use that simple calculation to say there does seem to be a difference in the numbers of different colors in different bags of M&Ms. Now, this is a very general way of doing this. And in fact, one of the ways that I would do this if I wanted to do it properly is I would actually look at the numbers in each bag. So there's a total for each bag, as well as the total for each color. So you can see that there are total bags and total colors. So what I can do is I can use each of those two values and my total number of M&Ms all up in all of the bags and use that to do a calculation. Now that will give me a much more complicated table, but it will give me a better estimate for my chi-squared test, because now I can see that they aren't all the same, but are all the bags giving me what I should expect. And you can see that some of the numbers, even in the distribution of one particular color, are quite different in some of the bags. And so that would be a better way of doing the chi-squared test. Just like with the t-test, there are some assumptions that we make when we're using the chi-squared test. And the most important thing that we need to remember is there are two categorical variables. We need to make sure that we're using categories when we look at this. So numbers and colors is fine. Categories, two or more categories or groups for each of the variables. So in the situation with the M&Ms, we have 6 different colors altogether. So that's definitely more than 2. And then you're also looking at things like counts, or you're looking at rankings, or you're looking at all sorts of different things. So you want to make sure that you've got at least 2. Obviously, if there's only 2, you're narrowing your range of expected values, but that still gives you something that you can use in the calculation of your chi-squared statistic. Probably importantly, and where some of these things that I've talked about today have broken down a little bit in these last 2, independence is that there's no relationship between the subjects in each of the groups. That is, you can't link them in any way like you would if you had a pre-test and a post-test. So it's the same person in each of these 2 groups. So they should be independent. And again, sample size is important. We want to make sure that we don't have sample sizes that are too small. Obviously, we've got to have a value of 1 in each of our categories, because you can't have zeros. That's not going to work for our chi-squared test. We can't expect zeros in our categories. We want to expect something in each of our categories. In fact, the expected categories are probably better if you're wanting to look at a valid result of being at least 5 or more for most of your cells. So this does make me question my own result around my modes, and so probably I would be needing to think about some other tests. The most important thing is that you have a play with some different sets of data to try and get an idea about how you might use this particular statistic and and what you're going to conclude when you find the calculation and you get a p-value, and what's that telling you about that set of data. The most important thing, of course, is that when you collect your own data, that you can think about what is the most appropriate test that you can use. And so perhaps one of those that you're going to consider is the chi-squared test. Thanks for watching.